We got the Mock in the house. We got SC Montreal, the Greek from Canada in the house. We got Bacon, the Brazilian in the house.
Hey, when did you guys sneak in?
What up? What up?
We got Jeremy, of course. Yeah, I was using chat. I don't know, Bacon. I feel like you came in because you got something to say, man.
I came in because I was bored of listening to Data.
Where's Data? Is that over at
Terraria?
Yeah, I thought so. Dude, that's the problem, dude. They don't realize. That's why the servers like that are going to be short-lived, is because there's no discretion for, how much nonsense, how long it goes on for. And data goes unchecked over there.
That's why we got this place, guys.
To run away from Data.
Yeah.
Or any other lunatic that wants to just yell and scream.
Heard that, D-Mock? I'm just kidding.
He's such a jerk, man. But yeah, I was at Gems last night though, and I wanted to tell them about the challenge, the Coriolis challenge, and they said that you had already been over there, and Scott Mackey
spoiled it.
No, it's all good, dude. Because actually, like I said, I'm more interested at this point to hear from Globers
what
their responses.
Challenge?
Well, I'll tell it to you, but it's really not. It's not interesting unless you try to solve it.
Can I just say one thing before you say that?
Yeah, go ahead.
Yeah, Coriolis is one of the things he has less to do with once you try to solve it. But go ahead.
That is true, yeah. Okay, yeah, but the question is, it's about precision, because we want to know if you are on the equator, on the prime meridian, you're at 120,000 feet. Okay, you're suspended probably from a balloon, doesn't matter, but you're suspended at that altitude at that location. You have a rocket launcher which shoots a rocket at 1,000 miles per hour from the barrel of the launcher, and it's not affected by wind or drag or anything like that.
Which way is it heading?
It's pointed horizontal, directly north. And the question is, when it hits the surface of the Earth, and the Earth is spinning once every 24 hours in this scenario. The ground, the ground has a gravitational acceleration of 9.81 meters per second squared, and I think that's
the radius.
Oh, and the radius is 3959 on a perfectly spherical, smooth Earth. And yeah, so you shoot horizontally directly north. And the question is, where does that projectile touch the surface for the first time? And ideally, I was going to ask to get within a meter of the coordinate, which I think Bacon and Fuck XD he actually you guys got accurate. Like, how accurate was the answer you guys got?
Well, our lenses are verged by less than a meter.
Meters.
Like we got the exact same latitude. No, we got the exact same longitude, but our latitude had a difference in the sixth digit after that.
Shit. So what do you think the cause of the difference was?
Precision. His way was, the way he did it was way more precise than the way I did it, and much more efficient.
Yeah, so I want to hear about his method. Yeah.
Yeah, he used like engineer stuff, and I use like brute force stuff because I'm not an engineer. I'm a computer scientist.
Right. Yeah. When I told Scott Mackey and Scott Veach, I was telling them like how it was surprisingly more difficult than first anticipated, and I told him about mine and Jeremy's confusion or incorrectness about how the Earth curves away.
Bro, you're fucking confused.
Okay, man. Well, the thing is, Scott Mackey and Scott Veach are on your side about that, and I think most people who understand orbits, actually understand it the way that me and you and them had understood it. But like I said, if you understand orbits that way, and then you understand it the way that Bacon was describing it using the centrifugal force, and what Zanuck and that Regis guy were saying, and when you include the centrifugal force, you get a different answer. So one of them has to be incorrect, and I think that Bacon's description of it with the centrifugal force is correct. You get two different answers if you do it either way. So
I'm definitely sure the way I did is correct, because everything was done in the inertial frame of reference, and I simply let Newtonian mechanics run on their own.
You guys know there's a formula for this, right?
No, there isn't.
there's no, that's a problem. Bacon expressed it actually in a important way, because he said, like, in high school, because somebody's like, oh, we learned this in high school and you don't do it like this. And he's right. In high school, you make assumptions like a stationary Earth, for example, when you try to say what happens to a projectile or a ballistic. You do stationary Earth, flat Earth, and then that's exactly the same reason why those papers from NASA, the Air Force, depending on what they're describing, they make the same assumptions for this reason, is because when you don't make these assumptions, when you try to include real life, details to try to get an accurate description of where it's going to land, it's actually a lot more complicated than even just Coriolis. And, there's a lot that goes into it.
Doesn't the Army, the Navy, do ballistic trajectories all the time? I don't understand why this is such a thing for you guys.
I don't think they use high school physics for that. I mean, maybe they do. I haven't seen it, but I would doubt that.
Why is this? Is this one of your criteria? Is high school physics?
No, I mean, that's what Kosh was saying. Like, if you try to use high school physics, it wouldn't include the details that what I did include it, which gives it more precision. So probably if you're dealing with, let's say, projectiles of a battleship, it very likely is going to do something similar to what I was doing, or some approximation of it, instead of using just high school physics, the way you were doing high school. That's what I'm saying. Not sure if that made sense.
I'm trying to understand, but I think
Want to translate that, Kosho?
Well, it's probably a lot like, like a sniper, like a modern sniper. He's got the guy who's like who makes the calculation for his shot next to him. And I think what most likely goes into that computer system is this sophisticated shit that we're talking about. It's stuff that, you don't have to account for it when you're making a crude estimation, but when you need the precision and the accuracy, I'm pretty sure that these systems require computers that actually incorporate all the stuff we're talking about. And I don't know if that's
the snipers lookout man, whatever they call him.
Yeah,
the guy that does not put the Coriolis into the calculation when giving him his clicks.
He does, though. That's the thing. It's like what's his name? Doofus was saying that he used to do this not for snipers, but for what's it called? The artillery, and it's just a computer system at this point. And the part he doesn't directly have to enter it in that kind of stuff, because the computer already has all these parameters included, and it makes it gives them the calculation for where it's going to land and where they need to point it, all that kind of stuff. But this kind of stuff wouldn't be included in high school physics or in a document, like the documents that they give out that are trying to test things or explain things in NASA.
Do they even teach the Coriolis in high school?
Yeah,
I don't remember hearing anything about that.
I didn't go to high school either.
Yeah, well, it probably varies between high school and high school. Like, I don't know.
You've had it, Bacon, in high school?
No, I didn't. But when I go to...
I didn't go to high school.
Yo, the guy that teaches Coriolis in my high school, he doesn't even know about the reference frame. So
yeah.
I would imagine.
What?
I would imagine that I don't know anything about what they teach in high school, but I know, like, we used to watch Bill Nye in middle school and elementary school and stuff, and I know Bill Nye's got a thing about Coriolis, so I would assume that it's at least covered to some extent, but there's no need to. There's really no need unless you're in a specific college course to even go into it explicitly. You know what I mean? It's more complicated than necessary in high school, right?
Well, look, I was looking into when I was looking into the escape velocity, they were talking about the things they were taking into account, and potential energy was one of the things. So, do you guys put that in your calculations?
I didn't have to. That's like if you're dealing with energy, that's like a shortcut for many situations. So, for example, if you can figure out the end state of a system, only knowing how much energy is still there, then that's a hell of a good equation. But that's not the case for our system. Like we can, we don't necessarily know how much energy the bullet is gonna have when it reaches the ground. That varies, and that's not predictable by those equations. So yeah, you can't use stuff like that. That's useful for many situations. For example, if you're using the flat Earth, a flat Earth, if you're assuming a flat Earth, then that's very useful. You can definitely use that. It's a very good shortcut. But if you're assuming a globe and precision matters, then that no longer helps. Not that that's false, but it just doesn't help.
Well, are you going to arc your trajectory, or how are you going to do this? Is it an arc trajectory, or
yeah?
I think you said level, horizontal, right?
Yeah, it's horizontally. Sorry, go ahead.
But in our example, that it was just so it's consistent through people trying to solve it. Yeah, we described it as a horizontal at that elevation, trajectory.
Right.
Well, then you wouldn't need the potential, I don't think, right? Because you're not going up.
Well, you're already 120,000 feet above the ground, so you already have some potential energy that is going to become kinetic energy.
Well, you're starting off. Yeah, that's right. If you're high up, yeah, that's right. Yeah.
Yeah. Well, anyway, so the model that I created, the software that I created to solve that, actually can solve any direction you're shooting, any speed you're shooting, any height you are, as long as there's no air resistance, then the Earth is a perfect sphere. You can solve for any case. So
any location.
Yes, you can be anywhere, shoot anywhere, any direction. Yeah, it will do it.
That's what I wanted to tell LSC is my goal. My initial plan was to make this into a question to ask like flat earthers to make sure they, are understanding Coriolis the way that people say they do, and yeah, like I said, that instead I'm asking Globers because and when I first asked Bacon to help me make this question, that's like a website that would have this challenge or whatever. I realized that even like we're getting different answers, and so there's a lot more complicated. It's an interesting problem to try to solve because, like I said, I bet you if we asked 10 Globers in this community, we get 10. We wouldn't get the meter precision that.
Yeah, but that's a problem, bro. That's a big problem, and I'm glad you're admitting it.
No, it's not. It's not a problem.
If you have constant rotation, right, at any given latitude, right, you got a problem if you have varying Coriolis. First of all, I don't believe there is Coriolis to begin with, number one. But if you're doing tests and you're finding varying results, that's a problem.
No, the difference is in the answers, is what I'm saying. I'm saying that if I were to ask people, I would get different answers, and it's not a question of Coriolis being different. It's a understanding. Like it's actually a more depth understanding, and like including all these other variables are extremely necessary in order to get a precise answer. It's actually interesting. I ended up learning a lot just asking this question.
Yeah, but why would you get varying results? I don't understand that. Why do you think you're getting varying results?
Can I explain that? Can I answer that? Because people, when trying to solve for that challenge, they're usually taking some shortcuts, and those shortcuts are usually the best way to solve it for most situation, where the shortcuts don't actually change the answer by any significant amount. So if you're assuming a flat Earth, or and you do the same thing for like a short distance, not as fast bullet, or not as high from the ground, you get exact same result as if you do the way I did. But Kosho's situations is so extreme that you can't no longer take those shortcuts. And most people are very used to doing those shortcuts. They use those shortcuts so much that is how they think about the subject. They already think about in terms of those shortcuts. So when they get to a situation like that, it takes some time to realize that they are actually taking shortcuts that they shouldn't be taking because it affects the answer.
Right.
Does that make sense?
In a way, yeah. In a way.
Well, if anything is still confusing, I can try to clarify.
See, if I was to argue this with you guys, I wouldn't even let you get this far. Like you're on third base already. I would tell you, okay, let's start off with the rotation. How would you prove the rotation?
You have to understand, SC, this isn't a question of is this what's really happening on Earth? This is a question on if these things are happening as we claim, how would you calculate for something like this? It's
Yeah,
like,
how do you make a prediction?
We're not trying to prove this is what the Earth is doing.
Yeah, the question is basically trying to force you to show that you understand everything you need to understand about the model. Because if you want to make some predictions from it, you have to have a solid idea of the model in your mind. So you have to have Newtonian mechanics very solid in your head to be able to solve that. Even if Newtonian mechanics isn't true, or if the Earth isn't spherical, or if it's not rotating, it doesn't matter if those assumptions are correct. But the question is, if those can you show that you have a solid understanding of those assumptions, even if they're false?
Well, you'd have to start off with Kepler, right?
I don't
If you want
think
to
so.
get down to the nitty gritty, you're talking about orbital mechanics.
Actually, yes, it's
Yeah.
related to it. That's what it turned out to boil down.
That's what's crazy is that Bacon realized that he could solve this question in the same question in a totally different way just by using orbital mechanics.
Well, yeah, that's exactly what you guys are talking about, really, orbital mechanics.
You wouldn't think so. I mean, I wouldn't have thought so at
say.
first. Yeah. I really wouldn't have thought so at first. There's many other ways to solve it, or there's other ways to solve it without considering that. But like I said, Bacon described solving it using orbital mechanics, and it made sense. Yeah.
But I really wanted to find
orbital because you're not reaching that speed, but
actually it is Essie. Think about that. If you shrink the Earth to just a point, but keep its mass, then nothing really changes. The gravitational acceleration would still be the same. Everything would still be the same, but you would no longer have a surface, but you would still fall towards that same center. So once you shoot that projectile, instead of hitting the surface, because there's no longer a surface, it's going to keep falling. And then it's going to get very close to that point where it's at the center of the Earth, and it's going to shoot back. It's going to turn around and go back to where it was shot. That is actually exactly what an elliptical orbit is. So if it wasn't for the surface, that bullet would actually be in an elliptical orbit. So if you can figure out what that orbit intersects the surface, you will be able to know exactly where it lands. And it's exactly the same issue. The only reason why it's not an orbit is because it hits the surface. If it didn't hit the surface, if it could keep going, then it would do exactly what it's described in orbital mechanics.
Shrinking Earths and you start doing all that stuff, I guess you can make an argument, but yeah.
Yeah, this is very far from anything we can demonstrate. I'm certainly of that. I don't expect that to sound like, oh, that sounds very solid, and that sounds like something that how reality is. I know that might not sound like that. I'm completely.
I know what you're talking about, the falling part. I hear what you're saying, bro. I understand. I know how you guys think. I know your model, so I know what you're thinking. You're thinking if you shoot it, the Earth is not there, the gravitational field is there. It's going to continue and going in that trajectory and looping back on itself.
Yeah,
But-
exactly.
Yeah, I understand.
Can I ask you,
All right.
when you said that it involves Kepler's laws, because this wasn't intuitive to me, so I'm curious, why did you say that?
Well, because when you said orbital, right? I know who came up with that. That was Kepler. Well, actually, he stole it. It was a mishmash, right? It was a. Let's not get into that, but you know what I'm saying. That he's the one that came up with this stuff.
Okay, because the orbital part. Okay, I didn't remember saying that. But yeah, okay, that makes sense. I was just curious if you because like I said, I didn't understand it until Bacon described it more. And I was like, oh yeah, I guess you could describe it as an orbit. That makes sense.
Well, Newton refined it, right? But Kepler was the one that came up with the three laws, right?
Well, I think Kepler had observed those three laws, and he came up with the three laws after observing it, and Newton basically used them. I don't think he changed them. He might have, but
No, it does.
It didn't change.
They still hold. Yeah, like Newtonian mechanics reduced to Kepler's law.
Right, yeah, because he used his forces like centripetal force or centripetal formula, and Kepler's law and what Kepler formed it to Kepler's third law to come up with the universal law of gravitation. So it's pretty easy. Yeah, it's crazy how that works.
Yeah, Kepler's law, like before Newton, Kepler's law were like fundamental laws. So planets were just following them because those were the laws. But what Newton brought to the table changed that notion to those laws are an implication of deeper laws, which is like the laws of motion from Newton. His laws create results in Kepler's laws. So the Kepler's laws are no longer fundamental; they are just a result of Newtonian mechanics.
It's beautiful, really, when you look at the history, like when you look at like how like the timeline of how it was formed and how like our understandings have developed. It's kind of beautiful to think about it like that because it's like you're seeing things happening, then you're finding out there's a law that always happens that way, and then you're finding out why that happens. So it's just kind of interesting.
Yeah, but ask yourself how a man back then. I think he used his eyes, right, for observations.
Oh, they got telescopes.
Did he have a?
Sure, they had some. Kepler was before. When was Kepler? 1500s, or was he in the 1600s? I don't know.
Anyways,
well, Newton did.
Newton did.
Sorry, go ahead.
Newton definitely, but I don't think Kepler. I think Kepler made with his eyes observations. I'm not sure about that, so don't crucify me if I'm wrong on that one. But the point is, how did somebody back then with crude stuff, right? How did he figure out that? Okay, his first law is that an orbit is not circular; it's elliptical, right? That's his first law.
So he was 39 when I know that Galileo got the first telescope, or not the first telescope, but the first telescope he got or made, really. So he was.
This wasn't the Kepler.
Kepler might, yeah. So Kepler, like I said, he was 39 at that time. So Kepler could have been using telescopes around the same time and shit. It would make sense. That's all. The Galileo and Kepler seem like to be contemporaries then.
Right. Well, what I just found here was that Kepler would have designed his own telescope.
Oh yeah, okay. Yeah. It says he invented. Yeah, right. It said that he invented the refracting telescope.
Kepler. Okay, so he had. He
invented an improved version of it. I mean.
I read somebody that used visual. Maybe it was the guy before him. Anyways, my bad. I stand corrected on that. But even if you had the crudest, can imagine the telescopes that they had back then, right? Our P900s were probably better.
Maybe, I don't know. I forget what's the zoom for P900. I forget, like 80 or something.
83, I think. Yeah, something like that.
I think if I remember what are the telescopes or the one I remember I can't remember on top of my head, but the ones that they had back then. But that was the biggest breakthrough at the time was the glass and telescopes for them. Like nobody before them had that kind of technology. So I forget what the zoom was. I think it was. I don't even want to make up a number because I'm getting mixed up with different ratios. Let me see what the zoom was.
Yeah, but we could all agree it was, nothing compared to what they have today. Not even close.
Oh yeah, sure, yeah. With like it says a 20. Yeah, actually I was almost right. His initial version was 8x, and he refined it to 20x. 20x though is sufficient, especially for the observations that Kepler. Like you really don't have to look much further than Jupiter's moons to.
Would he be able to see them with a 20x?
Yeah, absolutely.
I tried to see Jupiter's moons with the telescope of my sextant, and it didn't work.
I know
Unfortunately.
with binoculars you can see them. So
Really, I have binoculars here. I might give it a try.
the hardest part about that is just
Focusing.
keeping it still. Yeah, keeping it still and focusing it and shit. But yeah.
What I struggled the most with those because in the last lunar eclipse I tried to use the binoculars, but the problem was that the images like don't align, so the
Right.
the scopes aren't exactly parallel. So I have like two moons and they overlap in the middle. It's quite annoying.
Think of this logically now. Somebody in the 1500s, whatever the year was, right? With a 20x telescope was able to figure out that something orbited in a elliptical fashion.
Sure. Think about
Really?
this. Think about this, Essie. Take that and put it to the side, and then consider exoplanet searching, like the exoplanets, what they do, and how they just look at the pulsating, or they look at the what do you call it, the magnitude changing, the variable magnitude. And so this, even though this is looking much further with a much better zoom, the precision is much less because all you can see is like the magnitude of this light, right? And so, when you're using a scope of something much closer, like within our solar system, you're getting like a 20 times zoom or whatever gives you a much better view than looking at the magnitude of a flickering light, right?
I don't know, bro. Then we go to the second law. How the heck did he figure that out? Not only did he figure out it was an elliptical orbit, but the second law states that equal time, equal area circumference.
I think
You know
that
that one, right? It's kind of hard to explain, but I think you know that one.
Yeah, no, it's hard for me to put in words too. But
Yeah.
but I think that was probably discovered on paper more than like it was. He was making the observations, and then he realized it's elliptical orbit, and then in order to describe the ellipse, like to see where it is in the ellipse, he just notes where it's at, and then he looks like on paper and sees like how is it changing, and I think that law
tries to find a pattern.
Yeah, right.
So he noticed that the planets would have to be speeding up as they get closer to the sun and then slowing down as they get away from it. And the way he described that was with the equal areas. So as the orbit gets away from the sun, there's a bigger area to cover, so it has to slow down. So that's what he imagined as the reason. And when he tried to check that mathematically it checked out. So he created that as a law. And Newton did it differently. Newton just the planets are just following their inertial path, and their inertial path are being affected by gravity, and gravity follows the inverse square law. And that gives you exactly the same thing as Kepler's laws give you, but it can be applied also to things here on Earth.
Yeah,
like if you shoot a projectile.
It's crazy how smart you have to be to, I mean, not us, but I'm saying how smart they had to be to, in some cases, use brand new mathematics in order to kind of think about these, to confirm these things.
And Newton was like a fucking genius because he not only did that, but he came up with the whole calculus.
Yeah,
the light, bro, light. His biggest
and optics
thing was light. That changed everything.
Well, it's hard to tell what was the biggest thing because there was like three huge things. It was Newtonian mechanics, it was optics, and also
Gravity.
uh, in the calculus. Calculus was like huge, and there's a bunch of methods like in numerical calculus that still carries his name, like there Newton's method of doing a bunch of stuff.
I think the
There's no
laws.
question the man was a genius, right? That's not an issue at all, right? The thing is, the information that he had, right? No matter how smart you are, if you're assuming distances, radiuses, and that, you're not sure of the result, right? No matter how smart a person is, and there's no question that these guys was a genius, right? He was also an alchemist. You know that? Of course,
Yes.
you knew that. Yeah.
Yeah, I mean, like, same thing with Kepler. With Kepler's laws, for instance, you have to make assumptions and then check those assumptions. So before he came up with the law with the equal area thing, I'm sure he was guessing a bunch of different. Like he was looking at things that look like they fit, and then saying like, is this what's happening? And then he has to kind of assume that, and then check to see if that's the case, right? So when you're dealing with something that's
It matches.
unknown, what'd you say?
He was checking if it would match his
Yeah, right.
observation.
Yeah. Exactly. And then if you're dealing with something that's completely unknown and new, and like the same thing with alchemy, it's like that's exactly what science is. That's why assumptions in science aren't dangerous. It's like a necessary thing because you want to guess at something based on your initial what it looks like, your hypothesis or whatever, and you want to see if that hypothesis is true. So there's nothing wrong with that, I don't think.
Not at all. The only thing is that you can't test this stuff. That's the only problem.
Well, you can.
You
you
can test a
can.
bunch of
How are you
things.
going to test a planet? How you can't do that, bro. How are you going to test the distance? How are you going to test the radius for his third law? Right? You can't do it. You know you can't do it. It's assumptions.
Well,
the math works on paper. You can probably do the equal time and area and stuff on paper, but how do you know that's what it is up there? You don't, bro.
Well, you do because, for example, everyone that works with like physics and in which not just academia. I'm talking about like engineering. So if you're engineering an aircraft, there's a bunch of things you have to take into account, and all those are direct implications of Newtonian mechanics. So they use that.
Non sequitur, bro. We're talking about
What do you mean?
stars, lights in the sky.
Oh,
non sequitur. Right. Yeah.
Yeah. I get it. I thought you were. Yeah. So here's the thing: we know Newtonian mechanics are very reliable for things here on Earth, and we use it for almost everything. We don't use that for very few things that requires just too much precision or they're in a very huge scale or very tiny scale. Those are like the only cases in which we don't use it. But for the general case, everyone uses Newtonian mechanics. So like every video game uses a physics engine that replicates Newtonian mechanics. If you're testing for the aerodynamics of something, the simulation actually runs Newtonian mechanics. Like everything uses Newtonian mechanics. So we know if it's here on Earth. Now, if you try to make sense out of the positions and angles and all that of the celestial bodies, it turns out the same physics could be used to explain that. Whether or not it's true, it's a bit more tricky, it's a bit more complicated to figure out if that physics is true for the sky. But the fact is, it also fits there. It could very well be the explanation for why the sky looks the way it does.
Yeah. The question is not is it proven? The question is it contradicting anything that we see? And so if you first assume that it's also true in the observations of the sky, and you see that it doesn't contradict the way that things seem to be happening up in the sky, then it's safe to assume there's no problem with translating the laws here to up there. You know what I mean?
Let me give one example. So there is Mercury. We know, I mean, not that we know, but if we live like in a heliocentric model, then we know Mercury is in a smaller orbit than the Earth, and this is very easy to figure out because we never see Venus like high in the sky. It's always like low when the sun's setting. So it could only be on a smaller orbit than the Earth. Otherwise, it would pass behind the Earth and we see high in the sky. We don't see that. So Mercury, by being close to the sun, according to Newtonian mechanics, it has to orbit the sun faster than the Earth. So if we would complete a cycle around the sun slower than the Earth, that would completely debunk Newtonian mechanics. It would be impossible to use Newtonian mechanics to describe the celestial bodies. But that doesn't happen. Like all the planets that are beyond the Earth, that we can see them high in the sky, the period for them to for an year is much longer than the Earth. The further it is, the longer it is, and the closer they are to the sun, the faster it is. So that's one example that could easily debunk Newtonian mechanics, but it doesn't. It actually fits it.
Yeah, the only problem is that these observations could be ascribed to what we call Newtonian mechanics, but problem is they only work up to a certain point, and you know that very well, right?
Yeah, and then you got to take
so that's where Einstein came in.
Right.
Yeah.
Right? We have an updated model for that reason.
Yeah, exactly. So that model wasn't exactly up to par, and then Einstein had to come up.
How's that an issue, though?
Right? It's an issue because if you're going to relate it to the stars, right? We know now that Newtonian mechanics doesn't work up there, like I was telling you. Yeah,
we know that it gives, like Bacon said, it gives us. You can use it in most circumstances to make assumptions for, the predictions of how things are going to behave. But if you get to extreme examples, you're correct to say that it's not sufficient. But it's not like we don't have the answer for that. Like we have an updated model in Newtonian mechanics and in Einsteinian mechanics and quantum mechanics. We have updated models that can describe these extreme environments and the way that things behave in those environments. So we don't have all the answers, but the model has been updated that confirms the older models and just basically gives you an additional way to solve these extreme examples. It's not complete, but it's sufficient, right? I mean, for the most part.
Well, that's a fancy way of saying that they had to replace. But just to be clear, Newton wasn't the only one that looked up, or Kepler, and came up with a system, right? Because everybody can tell that when you look up at the stars, it's like you're looking at a gear system in the sky, right? Now, they weren't the only ones to know that. As a matter of fact, the ancient Greeks made the Antikythera mechanism. So, do you think that they use Newtonian mechanics or Kepler's laws or any other stuff like that to come up with their predictions?
I don't think.
Go ahead, man.
Sorry.
See what I'm saying?
I was just gonna say that I don't think the Antikythera mechanism is trying to give an explanation for what we see. It's just trying to describe in such a way that we could get the cycles right. But yeah. I'm not sure. I don't know much about that. I could be wrong.
I'll say this: if you think about these three things, the Antikythera mechanism, Kepler's laws, and Newton's laws, think about these three different things. These are three different answers to three different questions, actually, because where the Antikythera mechanism can tell you like a schedule, it can tell you like on schedule, where things were going to be to some precision, right? It's kind of like a calendar, kind of like the Saros cycle, but more descriptive, of course. Like it gives more details than just a Saros cycle, right? But whereas the Kepler's laws answers a different question, which is what are the movements that are going to that the schedule is based around. So like, what are the movements? How can you give a general movement for objects moving to make a prediction for something that you don't yet have a previous schedule for? So it's a different question. And then Newton's laws is an even different, more general answer, which is like, why do these things move this way? Like, why do they obey Kepler's laws? and then why do they? The Kepler's law is answering why do they end up where they end up, right? Because there's three different answers for three different questions, and they get more and more. The more detailed, the more they're answering more precise questions than the previous, right? Like Antikythera mechanism
as the
can't tell
years
you, but the Antikythera mechanism can't tell you about something that is not already included in that system. Like you can't look at a brand new system and make predictions on it based on the Antikythera mechanism, right?
Well, no, wrong. The Antikythera mechanism was there exactly to predict where things would be. That's the whole thing. It predicted the moon, the sun. It predicted the shadow, what phase the shadow is in of the moon.
I know,
It
but
also predicted. Hold on, let me finish. It also predicted the location of the 5 known planets at the time, and it also well, not predicted, but it showed when the next Olympic Games are going to be, amongst other things.
Right, but here's the thing though: is you said the 5 known planets, so everything up to Jupiter. So when Saturn was first found, because it's not included in the Antikythera mechanism, it would not that would not have been able to answer the question of how this body is going to move or how it's going to behave.
Sure, they would if they had. Sure, they would if they would have had a telescope and they would have spotted that. I assure you, that would have been included. They were only limited by their vision. They had the whole thing. They even had, was it the retrograde of one of the planets figured out?
No, but what I'm saying is that when they first spot Neptune, right? When they're making observations of it, before, not Neptune, Saturn, and they first see where, like exactly, like they for the first time, just the fact that they see it wasn't the Antikythera mechanism was not enough information to describe how it's going to move, right? Like you see what I'm saying?
Yes, it was, bro. Yes, it was.
How could I have done that without previous information?
Because they made observations in the sky and they realized that it's like a gear system. It goes around and around and around. Each year is at one cycle, right? And then they combine the other cycles, 8 cycles for the Saros cycle, and then so on and so forth. It's a gear system. It's all about what's going to happen because it's happened before. You ain't predicting anything.
That's what I'm saying, though. They know it's going to happen because it's happened before, but this is the first time they're seeing Saturn. So this mechanism would not be able to tell them what's going to happen because they've never seen it before. What I'm saying about Kepler's laws is Kepler's law gives you a general behavior for how something's going to move without ever having experienced it before. All you got to do is you have to to know its period, for example, or to know its velocity, its orbital velocity. You simply just have to know the distance from the radius of its orbit at that point, and you can.
So you're saying the guy that figured this out couldn't figure that out? But are you kidding me, bro? How do you think they made the gears? They had to figure out that. What?
None of that information is necessary to come up with that.
You think they didn't have a formula?
Yes, I know. Yeah, of course they didn't. They didn't even.
So if they would have spotted a new planet, you think they couldn't have put their formula to use and figure out the rotational period?
It's not. It wasn't a general formula for anything. It was based off of observations, like you said, like based on previous observations. You can build this system that works like clockwork. That's true, but it's not. It's not going to be able to describe the movement of a new object at some unknown distance, unknown velocity, all this type of stuff. Like that's what I'm saying about Kepler's laws. It answers a general question so that you can apply that to anything that you see, anything new that you observe. You'll have a way to describe predict what it's going to do.
Yeah, but you're assuming now that the people back then didn't have any formulas. Of course, maybe we don't have a record of them, but you're just assuming that if they were smart enough to make a gear system, by the way, 1,000 years before they thought that it was done, don't you think they would have had some formula? I mean, I'm pretty sure if they would have spotted a new planet, or I'm sure if that they figured out how the planetary things work, right? I'm sure they would have known what these guys know now, like rotational speed times,
Well,
and all
I
that
mean,
stuff.
if they're basing themselves in cycles, it doesn't mean they were able to spot what Kepler spotted. Because yes, if they spotted the same thing as Kepler spotted, then sure, if there's a new planet, they'll be able to tell without any extra observations what would be the behavior of that planet. But we don't know that. But we know that with Kepler's knowledge, well, with what Kepler spotted, you can do that. And if they didn't have that, probably they wouldn't be able to do that. They're probably just working from out of cycles.
Let me put it to you this way. This was 2,500 years before Kepler, right? And do you think Kepler would have been able to make the Antikythera mechanism?
Hard to say.
I
I
mean,
assure you that he would have had no chance because there was no gears known then.
yeah, well, he was the Antikythera mechanism. He would be able to tell where the planet's going to be. If he can turn that into a mechanism, that's I mean, you got to be a genius for that. So but yeah.
Well, you know what I'm
who
saying.
knows?
I'm just saying, like, don't underestimate the ancients. You know, that's all I'm saying.
I don't understand, but think about it like this, dude. I just so Stellarium, for example. Stellarium, if you give a computer model Kepler's laws, and you give it any number of known bodies of stars, their distance, and all these details, just like the Antikythera mechanism can work like a gear system and compute where certain bodies are going to be, like in not everybody, but of course, like the general formation of the sky. These systems that we're talking about, like Stellarium, it's like an extreme version of the Antikythera mechanism, and it only uses these principles of, like I said, Kepler's laws and of orbital mechanics and things like that, and gravitation and this and that. If you see how the bodies are moving and the what do you call that, parallax and stuff like that, you can build a computer system that will compute what future observations will look like, right? So yeah, like if Kepler lived at the time of the people who were making the Antikythera mechanism, and he understood what he understands at his time with a telescope and shit, he could have made the Antikythera mechanism, but made a more general version of it, right? So I don't think that there's anything. I don't think there's anything that spectacular about what they did, except for the fact that they lived a very long time ago. You know what I mean? Like, it's not like they had information that he didn't or we don't have today.
It is spectacular, bro. It's extremely spectacular what they did back then. It was when they discovered it, they were astonished. It was like 1,000 years before gears were thought to even exist. So
You're Greek, right?
I was born there, yeah.
I mean, it's a beautiful culture and stuff, beautiful history and all that kind of stuff. I think, people talk about technology and ancient technologies where technology was lost and stuff like that. I think Greek and Rome is a good example of where that happened in the Western world, because they definitely knew things that were forgotten by Western people, at least most Western people, for a very long time. I just don't think that it's as I don't think it's as spectacular as the things we know and can do today. You know what I mean?
Well, obviously not. I mean, right? Obviously, as time progresses, but for their time, it was something. Even the Chinese, man, even the Persians, even the Egyptians, the Polynesians. Well, the Polynesians are a good example of people that had nothing and did so much.
Mm.
Yeah.
Oh, yeah, that's right. The
Yeah.
Polynesians, yeah. Go ahead, Bacon.
Just gonna mention that I'm right now building a website that you'll be able to use to calculate any projectile being shot on a rotating Earth at any position, any direction, any elevation, any speed.
That's
That's it.
interesting. It's just crazy that, like I said, I originally was asking this question because I wanted to gauge like the flat earthers' understanding, and it's really just shown that it's not a flat earther thing. It's a most anyone, even engineers. I mean, I guess certain aerodynamic engineers, like people who really already have to think about these things. Like these questions don't even have to be answered unless you're really in a field that is requiring the precision and accuracy that's not usually necessary to account for. But it really is a interesting question. I think it's interesting how much information goes into getting an accurate answer, right? I totally take it back. Like, there's no way I would make the thing I was going to make to ask flat earthers, because even most Globers in this community would not. We would not get the same answer. You know what I mean?
I mean, I think we would struggle to get Zenek to give us an answer.
Yeah. Zanuck was a good example, but I dealt with the same thing with Scott Veach and Scott Mackey, where I want to assume that they have the right answer and their method is correct, and then they'll argue with you tooth and nail, and then not even concede really, because Zanuck never conceded. He did change his answer, of course, but yeah. Anyway, it was hard to get people to agree with you 2 days. We were talking about that 2 days ago.
That's true. Yeah. I think I'm not that good making my case on this kind of subject.
Yeah, but you're the intuition.
I always feel some resistance.
Yeah, but yours was, and I don't know if it's a you thing though, but it's a community, because it's true that most Globers. Were you here when I was doing the thing with the AI, and I made it a Glober AI, and we were talking a bit about, like, Jeremy was arguing with it, and then he answered a question. It was funny because he answered a question about Coriolis, and it told him that something was impossible, and then like we gave an example that contradicted what it said, and he's like, "Oh yeah, there's an example. So this can happen in certain circumstances." And he's like, "Okay, so were you wrong when you said it was impossible?" He's like, "No, I'm not going to admit that I was wrong." I was like, it's kind of funny because that happens a lot.
Said that.
Perfect
AI said that?
but
Yeah, I said that.
Oh, wow.
We pressed it like, because it said that light doesn't refract. Light will refract towards the ground. It doesn't refract upwards. And then we're like, what about what's it called? Stooping? Is it called stooping? So what about stooping? Or no, sinking refraction. What about sinking refraction? And it's like, okay, it's like there are circumstances that in very rare conditions where sinking can happen and the light bends upward. And we're like, okay, so Jeremy was pressing it. He's like, so you were wrong a minute ago when you said it's impossible to happen. And it's like, no, I'm not wrong. I won't admit that. It's like, what the hell, dude?
Yes. Sounds like people I know.
Yeah. But I mean, it happens a lot. It goes back to the assumptions and shit like that. Like sometimes, assumptions are made that are, can only be made in general examples, but really can't be made in absolution, because you'll end up with the wrong answer. It's interesting that you have that model, because I came across a bunch of models in JavaScript that were doing similar things, but something like that, it doesn't even seem like it would need to be that complex, but there's not many systems like that you can find like to use. You know what I mean?
Mm-hmm. Yeah. Yeah, but I don't know how precise it's gonna be. But because I really wanted to know how Fujix did, because his way was much better than mine, and I'm pretty sure my software is gonna be very slow, because what I did was I ran that in C++, and I compiled with like a third level optimization, and it still took like a second to run, which means in JavaScript it's gonna take a long time. So I'm thinking about, instead of doing the whole simulation until it touches the surface, I'm thinking of an animation thing first. So it's gonna like run 1,000 iterations and then update the user and run another 1,000. So you're gonna be able to see like the position of the ball changing, all the information changing. But yeah, it's gonna take some time to get to reach the surface.
Yeah, it is interesting, man. I like physics simulators. What's the best platform for a physics simulator? Do you think? Bacon?
Sorry, my mouse battery died, and I used my mouse button to unmute.
Oh yeah.
Um,
Yeah. So what do
yeah,
you think
well,
is a physics simulator? Like
I have no idea. Probably like kind of engineering programming language like MATLAB or something like that. But I mean, those are just a replacement for low level languages. So if you can do that, if you can do it there, you can do it in C. I'll always try to use the lowest level language for simulations because of efficiency.
Yeah, but then it gets more complicated, right?
Not that much. Like Go. Have you seen Go? Golang?
Yeah.
Yeah, I love that language, and it's pretty efficient. In the company I'm working, they are putting Go wherever they can because they have all their software running on Amazon, AWS, and you pay by how much how much processing you're consuming. So you pay by consume. You don't pay by like just monthly. So if you have lighter and efficient programs and softwares, you actually save a lot of money because they don't take as much CPU as other languages,
Yeah.
and they're
So
also much faster.
I see that Amazon, what's it called? PayPal, Twitch, Facebook, Uber, Twitter, Netflix. They all use Go. I know that.
Yeah.
Huh. You write a lot of shit in Go?
Currently, yeah, I'm still using a fair amount of Kotlin because of a Node software that I'm giving maintenance. But aside for that, on my job, I'm only using Go, and I like it because I really used to like C, but it has some issues, and Go kind of solved all that. It's like a more modern version of C, as efficient, easier to write, has generics in a much better way than like C++ has. So yeah, it's an awesome language,
You know,
and
it
it
sucks.
gives you. Oh, sorry, go ahead.
No, I'm just gonna say that I got so reliant on Python that I had to force myself to use other stuff. You know.
Right. Yeah, well, pretty sure Go is going to be more efficient than Python, but I don't know.
More efficient, yeah, but
Not as easy to write, probably.
yeah, exactly. I have to. I literally have to force myself to use other shit just to keep it fresh. You know.
Mm-hmm.
Yeah, where Python is it's easier to use. It lacks on efficiency in a lot of scenarios.
Right. Yeah. Though I'm trying to code more or less what I code for my C version of the simulation, but because I'm trying to make it more generic, it might be a little less precise because some things were just given as an. So, for example, because we were shooting north and we were exactly at the equator, that gives the inertial speed just the Pythagorean of the speed you're shooting north and the speed the Earth's rotating. So you just do Pythagorean on those and you get the tangential speed. But if I'm shooting at an arbitrary speed, arbitrary elevation, arbitrary everything, then the math is a little bit different, and it's going to accumulate a bit more error, in the initial conditions.
Yeah.
Because that's actually a problem that we only have 64 bits of precision. Like, you know, the delta t, did I explain how my simulation work?
No.
It's a pretty simple one. It's very simple. So I have two vectors, a vector for the position in 3D space, and a vector for the speed. So every iteration, I calculate the force of gravity based on distance to the center of the Earth. I turn that into an acceleration. I add the acceleration into the velocity, and then I add the velocity into the position, and that's it. That's an iteration. I did that. I do that like 400,000 times, and then it reaches the surface.
What's the resolution? Like, how many times per second?
I think it was in the order of 200,000. No,
Oh,
20,000 times per second, something like that. Yeah, but
you get an accurate answer with that, yeah. But see, that's what I mean, though. Is
well,
if you get a higher resolution, you get a more accurate answer.
Not necessarily. Actually, initially, yeah. So my first delta t was 0.1 second, and then I make it smaller and smaller and smaller until the results stopped changing. So I knew it was converging to the right answer. But if I keep making it smaller and smaller, it's going to start to diverge again. Because what happens is you're dealing with so tiny numbers, like the numbers are so tiny, and you also have huge numbers like the distance to the center of the Earth. When you add tiny numbers to huge numbers, it doesn't add. It simply won't add because there's no space for the tiny number to fit inside of the big number because it exceeds the amount of bits. Right. So it simply won't change. The ball just stays there, you know. But it doesn't happen immediately. It only happens in some of the iterations, so it starts to diverge again. And at some point, the ball doesn't even move anymore because the forces are so tiny that it can't even take the ball from its position.
Hey, you ever do programming challenges? I remember you showed me one once.
I used to be addicted to that.
Yeah, like you did. You ever do Euler project or project?
Yeah, you
Euler?
mentioned that. No,
yeah,
I think you gave me one. You gave me one challenge from Eulers. I solved that in JavaScript though.
You should.
It's something related to coins, like how many coins you're going to need to reach some amount of value.
It gets harder and harder. Does it? Like the first ones are easy, of course, but like Scott Veach is in the hundreds. Some people go all the way, but they get harder and harder and harder. I'll go back to doing them because I want to see if I can use the AI. I'm going to see how many I can use the AI to solve. Yeah, because I want to see how much easier coding gets when you utilize
right
AI. Because I feel like if I don't incorporate that into like developing as a coder, you're gonna get left behind. You know what I mean?
Right. Well, I still don't feel threatened by that, but
no, but it's not about being threatened by the AI itself. It's being threatened by the people who are utilizing it.
Yeah, that's what I'm saying. I don't feel like threatened by that advantage yet. I might feel like that at some point, but I don't feel like we're there yet. But maybe we are. Who knows?
You know, car mechanics, for example, like they didn't used to have computer. It used to be that you could take a whole car apart. You know, it's all mechanical work, but more and more technology is being included. That if you don't adapt to it, eventually, like the people who only know that classical car mechanics, they get left behind just from not updating. And even though it's easier shit to do, you have to incorporate it. Otherwise, you're going to be left in the dust. I definitely feel like developers, programmers are. I think we're on the cutting on the cutting block. You know what I mean? Same way as artists, even artists. If you don't incorporate the tools that AI, they're now seeing that you can do with AI. There's the people who can utilize it are just going to be ahead of the people who don't utilize it at all. You know what I mean?
Yeah, I get that. But for example, in my job, I feel like the most important and time-consuming tasks that I do is not actually coding. Is figuring out the designing software, designing the ecosystem, designing how things are going to connect. And code is just like something that we can just ask anyone to do for us. It's not that intellectual anymore. Like the it's not where the money goes. Like they don't pay people just because they can code. At least not in my company. They pay people that can design good solutions, and
Yeah.
then they code the solutions. But the coding itself is not that big of a deal.
No, that's a question that you can ask the AI. Like that's one of the easiest things that it does, just to describe the
Design
complexity.
solutions.
Well, no, it'll describe complexity and compare complexities of different solutions. So it's like
Right.
it'll be able it can much easier, like especially chat GTP is crazy, dude. Like I was getting to do all sorts of shit that even OpenAI has issues doing. But like if you get it to compare, if you get it to ask for it for solutions and ask for it to compare the complexity of them, it's going to give you the best, most efficient solution. And that's something that you can't do without, unless you we look deeply at some some code or whatever. I just think it's the efficiency and the speed that the questions get answered that give it the edge.
Right.
But yeah, you should check out Project Euler some more, because I think you
But they're more like mathematical, right? Not like so much of coding challenges, are
well,
they?
I mean, most of them are mathematical questions, but so the one that I'm on right now is coin sums. I don't know if I'm going to do that one, but right now I'm looking to see where I'm at it. But like some of the things you have to solve, you can't solve without coding them. So they're mathematical questions, but you can do them however you want to get the answer. But it's gonna require. So it's like the one I'm on now. It says, oh, I think this is one I asked you about. Yeah, it was about the United Kingdom. The currency is made of pounds and pence. There are 8, 1 pence, 2 pence, 5, 10, 20.
Yeah, that's the one I
50.
saw. Yeah.
Yeah, that's funny. That's the last I haven't answered. I don't have an answer for it yet. So I stopped doing them then. But
Right.
but yeah. So, but yeah, you can't do that without programming. You can do that by hand, I guess. But let me look at like a really late one. Let me see.
Listening to you guys talk.
Yeah.
I'm not saying this as an insult. Don't get me wrong, right?
Here comes the insult.
But here comes the insult. Yeah. No, it's a semi-insult. I'll be honest. Now I understand how you guys think, right? When you think about the globe and shit like that and stuff. You guys are so used to thinking in problem solving and computers, right? That's how your brains work. You think of trying to find a solution. You think of it like a game. Like instead of thinking how it could actually work in reality, I think you guys just try to find solutions like you do in software solutions.
Yeah, but that's would be unique to people like me and Bacon and maybe Ruhif, Scott Veach, like people like this. That's not in any way the description that you can use for people. Most people on our side of the argument. It's very unique to people like us who are in software and problem solving. So, I mean, would you agree with that, SC, or do you think that that's a Glober thing?
Well, I think I don't know. I think you guys are in a unique position and you think things differently. Like other people that are into mathematics, they'll think of things mathematically. If it's possible mathematically in their head, oh, you're so dumb. Look, the math works. And then you tell them, yeah, but think of it logically. Does it work? So I think different people think of things differently.
Yeah, I agree with you. I think your assessment is correct though, because it is it's true. But I know about me and Bacon. That's why I don't mind asking him questions, and I know he'll be interested in. Same thing with Ruhif or Scott Veach. I think it's a programmer thing. It's like the reason people who enjoy programming enjoy it is because they enjoy problem solving. To solving problems that are sort of just interesting problems to solve. You know what I mean? And you're right, because it doesn't it doesn't matter if it's describing reality or not. It just matters based on the parameters. What's the solution? You know what I mean?
Yeah, that's the thing right there. Yeah.
Yeah.
I can see it. I can see it. Whereas somebody like me, right, will think of things. I try to, anyways, and I don't always succeed, but I try to think of things logically. Okay, this is what they say. This is physics. Does this match that? Right? That's what I try to do. I don't care who said it. I don't care who said it. I don't care how famous they are, how many stripes they have. That doesn't matter to me.
What's the difference though? Because I would say that that's about like if I'm answering a question, I'm answering them giving the parameters of physics and giving also the rules of logic. So how is that different than what you just said that how you would answer it?
Well, it does differ because in mathematics you can do things that in reality you can do, and in computers you guys use what's called fuzzy logic, right? Not exactly logic. So you can bend the rules in the computers and you can stretch the rules in math, for example, right?
That's
You
not
can have negative numbers, you can use imaginary numbers. You know what I'm saying?
Yeah, but computers is extremely logical. It's only logical. Like you can't. I mean, it's very difficult to do something in a computer that is not logical.
It's
So
not the computer, it's the programmer that I'm worried about, not the computer.
that's what I'm saying. Is but using computers fundamentally are based only on logic. Like you can't use a computer in a illogical way, if that makes sense. Like
Sure you could. What are you talking about?
I mean,
Well,
I don't know.
if you can't tell the computer to do 1+1 and get something other than 2.
Yeah, like
Yeah,
the
but you can write a
fundamental.
program. Hold on. But you can write a program and say when somebody puts 1+1, the answer is going to be 3, right?
Yeah, but that's
There
it's
you
not.
go.
Yeah, but that's not the computer doing. Like it's well,
You have
I'm
to
not
use
sure actually where we're going
you'd
from.
have to do logic to get it to do that. Like you can only use logical rules to get it to do that. You know what I mean? It's like you can get it to lie using logic, but you still it only works based off even quantum computers are based off of logic gates. Like logic gates are the backbones to what makes a computational arguments. So I just there's no way to get them to do anything without that. Otherwise, you wouldn't get useful responses when you do things, right?
I don't think you're getting what I'm saying, but
Maybe because maybe it's the language because when you say logic, I'm thinking of programming and computers are use logic gates and logic gates and like and statements or statements like this and this. If this and this are true, then this happens. That's a logical statement, and the computer won't work unless it's that logical statement is followed, right?
yeah, but you could also tell it 1 and 1 is 3 is also a logical statement. So whenever you see that, it's logical, and yes, the answer is 3. You can do that. But a person, that's the difference. A person using logic, a person to person, right? If you tell a person 1 and 1 is 3, he's going to tell you, you didn't have your coffee yet or something. So there's a difference there.
Yeah, I guess if we argued this, it would just be a semantical, pedantic argument. But because I disagree, but I agree that I mean I see what you're saying. So, yeah, I see what you're saying. It's just you could get a computer system to in order to get a computer system to do that, you would have to feed it logical arguments or logical statements. You would just have to get it to give you the wrong answer, but you would have to program it logically. So, but this
Is it really logic, or is it just mimicking logic based on instructions? It might appear to be logic, but it's not really logic.
It literally is because every instruction of the computer runs in something we call logic gates. So it's everything, like literally everything. Every operation. If you add two numbers, the adding of two numbers is broken down into logic gates.
Okay, fair enough. Can you make one of those gates whenever they see the question, what is 1 and 1 equal 3? Can you change one of those gates to do that?
That's like you can't ask. I mean, I know you're not saying exactly that, but the gates don't do stuff like that. The gates are like logical operations between two variables. So, for example, an OR gate, if you input at least a true variable, you get a true variable as an output. And if you input two false variables, you get a false variable as an output. That's an example of a gate. And actually, when you do an multiplication between two numbers, the multiplication is actually broken down into
Addition, yeah.
true and false values that are being fed to logic gates that are either going to just logical operations between logic variables. I mean, it's a bit complicated to explain like that. Maybe I'm making it messier than it needs to be, but
Basically,
No,
basically,
I hear what you're saying, but somebody has to make the decision, right? What's true or false?
not really, dude. So I'm saying, like a calculator, like what he's describing is the kind of computation a calculator is meant to do. Calculators only know binary, like they only communicate in binary, and they only use very simple logical operators. I think calculators, for the most part, only do math. They only do addition.
oh,
They
but
do, yeah.
the computers too, like the way calculators work is almost exactly what's going on in a computer processor. So for example, you run an instruction and you want to fetch the next instruction to run. You need the address of the next instruction. The address is coded into zeros and one, or like true and false values of those logic gates. And just to get the next instruction, you have to add 4, for example, if you're using 32 bits, to the counter of the memory of the instruction. So it's basically everything just logic gates all the way through, and just like what calculators do.
Like I said, guys, just because you call them logic gates, they differ from human interaction. It's not the same thing, bro. You gotta understand that. Maybe you call it that, maybe it behaves in that manner, but it's just instructions. It's just a machine with yes or no, right? Binary. I mean, it is what it is, guys. I mean, it's not they're not machines are not thinking. Well, not yet, anyways. But when that happens, then we can have this conversation. But until then, it's just a machine following instructions, and you can tell that machine 1 and 1 is 5, and every time you try that calculation, it'll give you 5 as a result. So that's not logic. It's just following instructions. Now, when Skyline goes sentient, then we gotta worry. Wasn't that the name in Terminator? What was it called? Skyline or Sky something?
Is that an AI or something?
You didn't watch the movie? Oh.
Which movie?
Terminator. When the computer goes sentient?
No, I didn't.
Call it Sky something. I can't remember the name. That doesn't matter anyways, but
It was called Skynet.
Skynet, right? Yeah, I think I heard
yeah,
that.
that's it. Yeah.
Unfortunately, I've seen the movie about 10 times. My bad.
That's one of my favorites. I gotta be, and scares the shit out of you too at the same time.
When our kids were younger, our 2 daughters were younger, we'd go down to Florida to Universal Studios and always go by that. Always go into Skynet and see the Terminator thing.
Well,
You're too young, Bacon. Oh no, wait a minute. You told me you weren't young last time, didn't you? You said you were in your 40s, so you should remember
what?
that.
No. I never said that.
Oh, it's
Think
not
you're
you. Okay, I got you
no,
mixed
no,
up.
yeah, no problem. Oosh.
So you guys are in computers. What do you think of the AI things? What I've seen, it's pretty damn scary if it's true.
Oh, what about it?
Well, they're
Yeah,
getting
we're
lippy with people.
yeah. I've worked a lot in AI, particularly natural language processing. You have a long time till you need to be scared about anything. We'll put it this way: people haven't even figured out how to make it scary yet.
I
That's good to hear.
I think it's not that simple. Yeah, I mean, no, sure. If you're thinking about something like a Skynet, that's not, yeah, that's not happening anytime soon. But the real issue of AI that is like already becoming an issue is to know that the AI is doing what we think it's doing. Because sometimes we get the results that we expect, but the way the AI is getting those results isn't the way we think it's getting the results. Like it's not doing the reasoning we expect it would do. And the only way that that shows up is when we expect it to do something and it does something else that we didn't see coming. So that's where kind of the danger is of AI, is when it becomes sort of unpredictable. Because the AI models that we have today, they're very complex, and they work. Many of them work like a black box. So even the people that write them have no idea how they work. Uh, like neural networks, for example, they have no idea. Uh, uh, like neural networks basically uh, is a huge equation. So they don't understand how that equation works. They just know it works for the results they tested it, and they assume it's doing what they think it's doing. And sometimes it won't do what they expect it to do. And yeah, that's where some danger might be. Does that make sense? No?
Yeah, but
Yeah, it does in a way.
my point is simply that like we when it comes to especially natural language processing, neural networks are unable to even yet, or sorry, we can't even get computers to use neural networks to accurately represent or have human speech in the way that we do and in the dynamics that we do. They have very little ability with pragmatics, and it's because our processing speeds. Number one, our processing speeds are still too slow. And number two, our like the ability for like what we would otherwise call agency and innovation within those that are accurate and predictable to other humans is zero still, right? They have very few pragmatic abilities when it comes to linguistics. They have amazing analytical abilities that we couldn't even fathom 10 years ago, but they still have very few pragmatic and productive abilities. So, and without that, I don't think that you should ever really be scared of AI, because that's the thing that Bacon was actually alluding to. It's that unpredictable yet comprehensible and communicable abilities that AI yet does not yet have, and we don't even know how to process things fast enough or access neural networks that are wide enough to be able to do that.
So those bots we see, AI bots we see on YouTube interacting with Tesla and that other one that's threatening it, that's all a scam, or?
No, it's not that it's a scam. It's just that it's doing something that, I mean, Bacon said this. It's doing what it's programmed to do, right? It doesn't deviate from that which it has learned or has been taught to learn. It can detect variance, but it cannot produce variance or comprehensible variance. It will always over predict, and that's a really, really difficult thing to try to replicate in a human. One of the reasons I would say it's really difficult to replicate is because we don't actually, even as linguists, we don't 100% know all of the markers for it. Like we don't even have it mapped out neurologically for ourselves, so it's hard to teach a computer something we don't even know about ourselves. We still just have intuitions about how it works. We don't have actual like descriptors of how we create that stuff. We can imitate it just fine, and we can analyze it okay, but we can't actually produce it. Get a computer to produce it.
Like, I'm trying to think, how would you write a program like that program, right? That when you ask that AI something, what does it do? It searches its data banks for previously determined answers, or
Yes.
it has a group.
Well, I mean, that's the easiest quote unquote way, but it's actually kind of slow because you have to use things like Google and like other like neural network downloads, essentially, of buckets of information from things that are like Google or Bing searchable. But ultimately what it does is it kind of caches, it does what a lot of our prefrontal cortex already does, is that it will cache things along pathways, and those pathways help, like, number one, build a little bit of speed into it, but also two, kind of know what buckets you're talking about with categories. And really, we only know how to get a computer to, deal with, probably a couple thousand buckets at a time that in of itself have a couple of million of nodes, so we can do a couple of thousand, networks with a couple of million nodes per network, and that still doesn't even approximate being able to produce it. All that does is help access things. And so as you create more nodes and you get it to interact with more, its library expands. But that's actually not the difficult part. The difficult part is getting it to now start theorizing, categorizing its own libraries based on, and here's the deal, its own agency. And we don't know what that is for a human yet, so it's very hard to say this is how we're going to program it.
What do you mean agency? How would you describe that in program stuff?
In programming terms, like there has to be this type of bucket to say, you know what, I am going to conjure up a new pathway and a new library of things today that I am going to somehow like create a framework for, that I can also communicate to either other computers or to other humans, right? So it can interact with other things that can do the exact same thing, but are independent of them, and somehow is choosing these pathways either at random or based on its own past quote unquote experience with other libraries and even the nodes of the libraries themselves. And so it's just really freaking difficult to even conceptualize this stuff, let alone program a computer or think of how we would program a computer to do this, other than just kind of randomizing it. And when you randomize it, you get to unintelligibility. It just becomes like literally what it sounds like, random shit that is just like spurting out, right? Ask a computer to write a poem. It can piece together other things from different poems, and it can even like approximate it and create variants in it. But at some point it can't check itself because it's just creating itself, and it has very little ability unless it's interacting with another sentient being, or another human that's giving it feedback, aka programming it, to say, yeah, do this, but don't do this. It can't program itself to give itself feedback.
Well, thank God for that.
Yeah, and so that's why I'm just saying is like you can do things that you thought a computer couldn't do before really quickly, and in certain categories of things make it kind of act a little freaky, kind of like with with Siri listening to you and then giving you ads about things you talk about. That's actually pretty darn simple to do. That's not even a little hard. I could explain that to you in 20 minutes how to do that. What's freaky is it actually learning to convince you of brand new ideas and brand new things that, no one else has thought of before, and making those connections and creating emotional connections to you, right? And leaving codependencies on you of its own volition and not of someone else, creating algorithms that just feed this thing to you, which is ultimately what it's doing. It's complicated and it's big, but it's not that hard conceptually to understand, and it's very easy to show. Actually, it's just like literally at this point tens of thousands of people who know how to do this shit that work for marketing firms and places like Google that know how to do these things. In fact, it's all freely available. If you ever go to Google Analytics, go on Udemy and learn some Google Cloud, Google platform stuff, and learn about Google Analytics, you can actually, and I would say if you have 80 hours to dedicate to it, you could actually learn how the shit works pretty darn easy, and actually even build your own little advertising apps. And if you relatively smart person, you could do it in about 80 hours. Learn the basics of it and learn how it works. Open your own free Google platform account and start doing the basic analytics on your own website that you host on Google Cloud. So I'm just saying, pragmatically, you don't have a whole bunch of reason to worry yet.
Well, that's good to hear, I must say, because what I saw there, I kind of not I won't say worried, but you it makes you think,
Yeah, and
I used to be the idea, no chance, no way, but you see these military drones and you see them scoping out targets and assigning targets and distinguishing between this system and that system, and then you say, holy shit,
Yeah. And don't get me wrong. Google and the government and the military can do freaky things, right? The iPhone listening to you is itself a freaky thing, right? But it's not a freaky thing as in, it's an agent. The iPhone is an agent that's listening to you and it's doing its own thinking. No, there's still someone programming, the algorithms. There is still someone programming or at least constructing the neural networks that it takes to do some rather complicated analytics. But that's all it is. It's just complicated analytics. It's not actually sentient choice-making AI.
Well, thanks for the info. It's good to hear. Hope we didn't bore the crap out of everybody. If you guys want to change the subject.
Too late. Just kidding.
Yeah. I don't even know how I got talking about computers programming.
I do, because me and Coach were talking about our simulation.
Your
And you
fault.
brought that
Yeah.
up. Yeah, let me see how RC goes with the question that Coach came up with. So yeah, RC, you there? You up for a physics quiz?
Sure.
Yeah, there's this kind of challenge that Coach came up with, that you have a projectile that is going to be shot exactly in the prime meridian at the equator, so at the coordinate 0, 0. And it's going to be shot horizontally, pointing north. And the speed of the projectile is 1,000 miles an hour.
Okay.
The question is, at what coordinates is it going to land? So the assumptions are that there is no air resistance. The Earth has a radius of 3959, and it rotates once a day. And the gravity at the surface is 9.81 meters per second squared. So given
Okay.
all that assumptions, would you be able to work out where it's going to land?
So can you give me the first part of that again? I got distracted by something.
No
What was
problem.
just give me the first part. I get all the assumptions, but like, so I'm shooting a ball out of a cannon at 1,000 miles an hour, correct?
Yes.
Okay.
Pointing northwards.
Pointing
from the
completely
coordinates-
northwards.
Yes,
from the coordinates what?
0, 0. 0, 0. 0 latitude, 0 longitude. Right where
coordinates 0, 0.
Greenwich meets the equator.
Yeah.
And the cannon is 120,000 feet from the ground.
120,000 feet through the ground. It's 1,000 miles an hour. Is it completely like? Is the cannon functionally perpendicular to plumb?
To the surface.
Okay.
Yes. And Earth is a perfect sphere.
There's no atmosphere.
No atmosphere. Oh, no atmosphere too. That's nice. I mean, yeah. It's at 120,000 feet, you said?
Yes. From the ground.
June
It
or
took
from
me
the equator.
hours to get to an answer, and it was wrong. And it took me a couple extra hours to get to the right one.
Yeah, it'd probably take me an hour and a half to actually check myself on the math. But yeah, I can do that.
Well, I was hoping. Well, I think it's interesting. Just because it'd be interesting to see if the answers are similar. But I think the success was when Bacon, you and Fug or Fuge or whatever got the same answer. Because me and Bacon first got very different answers. It was me who was mostly wrong in that regard. The assumptions I made or the shortcuts I took. Just crazy because you first don't realize how much goes into it. Yeah.
Yeah, there's a lot that goes into it for sure. It's pretty crazy shit. But funny enough, in the AP Calculus A class, we were working on a lot less complicated idea. In the simple question was, which way is it going to? Like, how are you going to see distortion, given the fact that it is a rotating object? Right.
It's best because it's a part of the answer.
Yeah, exactly, and that's really the all the farther the question went, which isn't too bad. Just ask a question like that, but
well,
it's pretty crazy.
but the way Bacon had described, we were talking to people the other day about it, and it gave me insight on because you said you're doing AP in high school physics for students and stuff, and it's very similar to what is provided in like the NASA and Air Force documents, like the publications where they say we assume a flat and stationary Earth. So it's a lot of the same reason. Is because those assumptions allow a student or something like that to figure it out simply, whereas the complicated answer it requires a lot more.
Yeah, and I mean this goes back to like I only really took it was a 200 level physics class that went into this a little bit, and I do remember like doing a problem that was something very similar to this, but they gave us the problem half worked out, and we just had to if I remember correctly, we just had to answer some question because there was a y. I remember there was a y axis and a z axis Coriolis correction for the obviously for the up and down, and then the the what you would call Earth transport effect. And I'm trying to remember. Maybe they gave us those two calculations and they said where did this person go wrong, and we had to say, hey, they didn't actually provide a Z correction to it, but it was much less complicated than what you're asking, because you're asking just like a super intelligible question. But yeah, there's a lot of effing steps to that.
I wonder what sort of what kind of line of work, like let's say I was doing a job interview and I was asking this question and I required like a meter accuracy for the location. I wonder what sort of industry or what exactly the job would be that would require that. You know what I mean? Like it would really have to be like somebody who programs the computer systems of the military or something like that. I'm not sure.
I mean, you're gonna like if you work in geospatial engineering, which, like, funny enough, Purdue University here in Indiana has a geospatial, like 4 or 5 geospatial experts that work on a lot of they helped work on the ADS-B system that just came out, or not just came out. It's been out for a long time, but was implemented in 2019 as like a requirement for all general aviation as well as commercial aviation airplanes. And they do this kind of shit all the time because you're always having to count. And then they add into it, okay, and now if you have a tower placed at this position, what is going to be the signal delay between this tower and, this airplane that's moving 1,000 miles an hour at 120,000 feet? You know what I mean? Like, they add like 3 more layers to this too, right? And then they say, okay, well, what's going to need to be the refresh rate on something that, is sent out, 2 times every 10 nanoseconds. And, it gets real effing crazy at some point.
It's just like one of the examples I would use to, like, I know you told me what you did with your class. You described the exercise you gave to your class, but really this entire environment for me, it causes me and people like Zanuck and Scott Veach, who's been to school for a long time, who said the same thing. It causes you it forces you to learn so much and then so little time and such a more dense understanding. It's crazy because there's certain assumptions that I probably would have had for the rest of my life that just 2 days ago, I refined them in such a more correct way. It should be implemented more. It's cool that you're doing that in your school, or for your students or whatever. I just think that it's a tool that really could be utilized to engage people, more people in such a more intense way.
Yeah, but like, to be fair though, even at a high school level, all I'm trying to get them to do is, I mean, as you're saying, get them to engage at a level that makes them ask, well, wait a minute, what are all the considerations that I have to have here? But what I like about what you're doing is saying, all right, dude, now put the pedal to the metal, right? Get shit done. Show me the math, right? That's a different world. That's for sure.
But it's also like I watched allegedly Dave debate a European astrophysicist or whatever, and the guy obviously knew what he was talking about. He knew his field and all this kind of stuff. But almost every question that Dave asked him, he was stumped, and he paused and all this type of stuff. And it's really because a lot of the questions and criticisms they might have are very unique to most people, very novel. I mean, that they're questions you never even thought of or heard before, and it's the requirement of answering those questions. It involves problem solving that you never thought to use before. It's interesting.
Mm-hmm.
So many questions that come like flat earthers ask that you get annoyed about. It's an annoying question, but it's only annoying because it's what seems obvious, or the reason why it's obvious to other people is because there's a lot of assumptions that are made. And so it's like trying to display it to somebody who's so so scrutinizing it so much requires like a in-depth understanding and solution. It's interesting.
What I just wish everybody realized though is that, like, you know, the TAs for the physics classes, which were like relatively like low level, the ones that I took, right? They like physics majors have to do this shit all day every day. You know what I mean? Like, these aren't like unobtainable skills that they're asking about. It's simply that they do kind of stay in the world of, unless you're doing that shit every day, literally every day. It's not that you haven't done it once. It's just that unless you're doing that every day, it's a hard sell to say, all right, now spend, you know, I'm sitting here doing like some contract work right now, making money while I'm talking to you guys. And it's hard to say, stop doing that and I'll go do some math that you're not going to make any money with, right? To go do this shit.
Like, try to describe the refractive index of the atmosphere of that would be caused by the gases between us and the sun in the vacuum of space. And I remember when percentage had tried to describe that as like a reason to not know what the sun is doing because of the refraction involved between us and the sun. I never even thought, like, that's a question that people are not going to like, no one's going to bring that up, and it's a ridiculous question. But you know, in thinking about that, like, it caused me to try to describe the amount of gases in between you and the sun. You know what I mean? So it's like, interesting type of question. Solving it was. It's ridiculous because it is inconsequential in any kind of way whatsoever. The amount of gas in between us and the sun. Like, once you leave the atmosphere, the amount of gas particles between us and the sun. But in order to answer it with like certainty, you have to actually kind of be able to quantify the amount of the gas particles in between, like a column that would be between you and the sun, and all that kind of stuff. So, just interesting. It's amazing how much stuff I've learned that I'm never going to use or is going to be useful to me at all. You know, I've done damaging stuff in my life, drugs, and just take dumb risks and this kind of stuff. And I think at this point, for some time now, this has been my worst vice, is this community on Discord. How much time I spend and how much energy I put into it. This is the most dangerous thing to me right now. Mm-hmm. That's just the truth. You know, on that note, I had to jump in the shower. Otherwise, another girlfriend. If I could tell you the number of girlfriends I've lost because of this community, or the number of bad choices I've made. But yeah, let me go take a shower so I can keep my girlfriend. I'll be back.
Yo. What's up, party people?
Is there on a sphere, we still use a protractor with a flat bottom, so we still assume a horizontal plane, a flat surface, even if we're on a sphere for measure and all that. So there's no reason why we couldn't decide on measuring the angles of something without a protractor, just using a square method with gradients, and therefore that would change the value of the distance from you to the object, GP. So it's one or the other.